Okay, we're going to start with molecular geometry on this video, and we're going to start with the most simple molecule that we can find, and that is this right here. Molecular geometry dictates that we put electrons as far away from each other as possible. We call that VSEPR theory. That stands for valence shell electron pair repulsion theory. So we have this molecule right here. Remember, the diatomic molecules were those in which there were two identical elements. So let's just say that this was Br2, bromine gas. Br2 has two identical bromine atoms that are connected by a shared pair of electrons. And so in this particular molecule, because they are identical atoms, this is going to be a nonpolar molecule. In other words, the electronegativity of bromine is going to pull electrons toward this atom, and then it's going to pull electrons in this direction as well, but they exactly balance. So we have an exactly balanced structure. We're going to call this the linear structure, so Br2. This is a nonpolar molecule, but if I take this molecule, this atom off, and I replace it with, say, for example, hydrogen, then the two electronegativities are different, and I'm going to have a polar molecule. So bromine would be nonpolar, but if I replace the bromine, say, with a hydrogen, I'd have a polar molecule. So we're going to start with the linear configuration. It's as simple as you can get. This is also linear. Here we have a central atom that's connected to two peripheral atoms, or two external atoms. The central atom in this case is linear with the other two atoms. There's a bond here and a bond here. I want you to think of this. This is also linear. I want you to think of the example for this particular one as Bf2. Bf2 with beryllium being the central atom and fluorine being the two atoms on the periphery. So beryllium here and fluorine here and fluorine here. Now, remember that with regard to the polarity of the bond, fluorine is more electronegative than is bromine. Beryllium. Make that beryllium. So fluorine is more electronegative than beryllium. And so this bond is going to be polar. If I look at this bond is also polar. But the entire molecule is nonpolar. Why? Well, because of the fact that this atom is pulling electrons in this direction with the same intensity that this atom on this side is pulling in this direction. So it makes the entire molecule, even though each of the two bonds is polar, the entire molecule nonpolar. So BeF2, beryllium fluoride, as the example of the atom of the molecule that's linear. So that's linear. Let's add a level of complexity now. Let's talk about this molecule here. This molecule also has a central atom connected to two peripheral atoms. But the central atom in this case is not linear. The central atom is not linear because of the fact that a lone pair of electrons is on the opposite end of the atom as these two, on the opposite end of the molecule as these two atoms. That causes these two atoms to be pushed further down, creating a bent molecule that you see here. A bent molecule. I want you to use as the example for this one SnCl2. SnCl2. Remember, there's an unshared pair of electrons on top. Now, so this we call a bent molecule, or a bent or angular configuration. An angular configuration. So here's an example of an angular configuration, or a bent configuration. We'll compare that to this molecule here. This molecule is also bent, or angular. In fact, it's more bent, or more angular. The angle is more acute. I don't know if you can see that on the camera there, but the angle is more acute because of the fact that there's not one, but two lone pairs of electrons. Two lone pairs of electrons that are on this atom here. We'll use as the example water, H2O. So we have oxygen here, hydrogen here, and hydrogen here, pulling electrons in this direction, towards the oxygen, because oxygen is more electronegative than is hydrogen. The two lone pairs of electrons on top are really pushing down this way on these two hydrogens, creating a very acute angle down here. So if this one was bent, this is more bent, but they're still called a bent or angular configuration. So let's move on now to the next type of configuration, and that's this right here. We have a central atom flanked by 1, 2, 3 peripheral atoms. The atoms on the outside are exactly symmetrical. So we call this configuration trigonal planar. Trigonal because there's 1, 2, 3 atoms surrounding one central atom. Planar because, as you can see, the atoms form a plane. So trigonal planar, this molecule. And this is the structure. It's BF3. BF3 is the example that I want you to remember for this structure. BF3. Remember that boron does not follow the octet rule. Let's compare that to this structure here. This is also trigonal, but it's not trigonal planar. This particular structure is called trigonal pyramidal. And trigonal pyramidal means that a lone pair of electrons on top is pushing atoms, this atom, this atom, and this atom, down away. Remember, VSEPR theory states that electrons are going to be pushing away from each other. So it pushes them away. This is called trigonal pyramidal. Trigonal pyramidal, this structure has these atoms, this one, and this one, pushed down as a result of the electrons on top. And the example that I want you to remember for trigonal pyramidal is ammonia, or NH3. So trigonal pyramidal. Once again, trigonal planar, trigonal pyramidal, what's the difference? The atoms here are pushed down because of the lone pair of electrons that are not present on the trigonal planar molecule. So that is that. The next one I want to take a look at is called tetrahedral. This structure is tetrahedral. We have a central atom and 1, 2, 3, 4 atoms in the periphery. We have this atom right here forming an angle here, 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 here. All four of those angles are the same. So it is a symmetrical molecule. If I look at each bond is polar. So for example, if this was, we'll use the example of methane or CH4. Methane or CH4 is a tetrahedral configuration. This bond here is polar. This bond is polar, this bond is polar, this bond is polar. So all 4 of the bonds are polar, but notice the molecule as a whole is symmetrical. It doesn't make any difference how I turn it. The molecule is going to be symmetrical no matter how I turn it, and therefore this molecule is going to be, as a whole, nonpolar. Each bond is polar, but the molecule as a whole, nonpolar. Tetrahedral, methane. Let's move on. Now, we're going to talk about this structure here. This structure is called trigonal bipyramidal. Trigonal bipyramidal. Trigonal because there are 1, 2, 3 atoms surrounding a peripheral atom. Bipyramidal because there's a pyramid on top. You can see the pyramid if you have 3 planes, here, here, and here, and a plane and 3 planes on the bottom, forming pyramids on top and on bottom. Thus the name trigonal bipyramidal. So a trigonal bipyramidal for this structure. And for trigonal bipyramidal, I want you to remember PCl5. So phosphorus in the middle and 5 chlorines. 1, 2, 3, 4, 5 chlorines flanking that central atom. Trigonal bipyramidal. The next one we call octahedral. One more level of sophistication, one more level of complexity. So we have a central atom. This is called octahedral, a central atom with 1, 2, 3, 4 atoms in a plane, one above, one below. We'll use as the example for octahedral SF6. SF6, sulfur in the middle, fluorine here, fluorine here, fluorine here, fluorine here. One on top, one on bottom. SF6, this is called octahedral. Octahedral, okay? We'll move on to the more advanced structures now. This is called the Seesaw Model. Seesaw Model has one atom in the middle, and then 1, 2, 3, 4 atoms that are in this position here. And the example that I want you to use for the Seesaw Model is SF4. SF4 has a lone pair of electrons on top. That's what causes these atoms here to be pushed down. And it forms like a seesaw that goes back and forth like that, thus the name. One last structure, the T-shaped model. In the T-shaped model, we have, and we'll use an example, ClF3. We have one central atom here. It's flanked by 1, 2, 3 atoms here, here, and here. Again, ClF3 is the molecule that I want you to remember. 2 lone pairs of electrons pushing these atoms down, and that's the T-shaped model for obvious reasons. It just forms a T-shape. And that's really all that we had for the molecular structure, and hope to see you next time. Thank you.